Welcome back to the next lesson on Chapter 8, which is rates and equilibrium. So we're concentrating on the rates section first of all. Just want to recap what we talked about last lesson. So this topic is about how reactions happen, okay? What has to happen to the particles for them to react. So if you remember, reactions occur when, well, what happens? How do the reactions occur? It's when particles collide with enough energy. Reactions occur when particles collide with enough energy. I mentioned this diagram, you see. It's called the collision theory. We've got these two happy particles here, look like they're colliding. It looks like they've got plenty of energy, so they are going to react. What we're going to discuss is how we can make reactions faster. So if we're going to make reactions faster, we're going to make them collide more often, we're going to make them collide more frequently, or we're going to make them collide with more energy. There's different ways that we can increase the frequency and the energy of the collisions. So if you're happy with that, I'm going to move on to the first way of how we can increase the rate of reaction. Okay, let's get started. So you're going to need some file paper. You're going to write the title, Surface Area to Volume Ratio. We're looking at how the surface area to volume ratio affects the rate of reaction. We're going to investigate the effect of surface area on the rate of a reaction. You might want to pause the video where you write the title and the objective down. So I know you've done in biology lessons, you've talked about surface area to volume ratio. Okay. The first question, how do you increase the surface area to volume ratio of a solid? Imagine we had a small piece of metal. What could we do to it to increase its surface area to volume ratio? Hopefully, you're right, we could crush it up into smaller pieces. To increase the surface area to volume ratio of a solid, we're going to crush it up into smaller pieces. Now that doesn't make more particles. By crushing something up, we don't make more particles. Have a quick look at this diagram. On the left, we've got marble chips, which they're the grey particles in the middle. So imagine we've got these chips of marble, large pieces of marble. If we crush it up into smaller chips, we don't make more particles. What's happened though? There are now more particles exposed, so more of the particles will be able to react. So crushing something up makes more particles exposed. And that's important because, I'm going to write this down, reactions only take place at the surface of a solid. Reactions only take place at the surface of a solid. So, the smaller the pieces, the larger the surface area to volume ratio. The smaller the pieces, the larger the surface area to volume ratio. So by crushing it up, we're going to increase the surface area to volume ratio. Now these two diagrams, you can simplify them if you want, but I think they're good diagrams to draw. On the left, we've got one large cube. It's got a low surface area to volume ratio. On the right, we've got the same cube, but we've crushed it up, we've made it into smaller pieces. It's now got a higher surface area to volume ratio. And we're going to get asked questions about why they would react differently. Which ones of these two would you think would react faster? That's right, it's the one on the right with a high surface area to volume ratio. And we've got to know why it would react faster. The first thing we'd have to say is there are more particles exposed. There are more particles exposed. So, on the right, there will be more frequent successful collisions. Now, this is a very, very important phrase. If we have a higher surface area to volume ratio, there's got to be more frequent successful collisions. And that's going to make the reaction faster. We've made the reaction faster We haven't made more particles, there are more particles exposed. So now there are going to be more frequent successful collisions. An example we would do if we were in school, we'd use marble chips. Now marble chips are made of calcium carbonate. They react with hydrochloric acid to produce carbon dioxide. Now, I'm afraid the arrow hasn't worked there. So calcium carbonate plus hydrochloric acid would make calcium chloride, water and carbon dioxide. And remember last lesson, if we want to measure the rate of a reaction, if it makes a gas, we can collect that gas and time how fast the reaction is making that gas. So we can find the rate or the speed of this reaction by measuring how much carbon dioxide gas is made every 10 seconds. What would we use to collect the gas? Well, last lesson we talked about using a gas syringe. Now sometimes we don't have enough gas syringes for everyone in year 10. So we use this system here where we have the reaction happening in a conical flask and then the gas goes into this upturned measuring cylinder and that collects the gas and we can then work out how much gas was made every 10 seconds. We'd try it with marble chips, which are large chips. We could try it with medium-sized chips and we could try it with powder. Why would the powder react faster? Well, because it's got smaller pieces, it'd have a larger surface area to volume ratio. But we'd prove that in an experiment. And here again is a picture. We've got the larger chips and the small chips. The small chips have been crushed up. They don't have more particles, but there are more particles exposed. Now what you're going to do, you're going to plot a graph. Hopefully you've got some graph paper. First of all, you're going to plot a graph of the volume of gas given off against time. Now I'll say this clearly, you'd want to have your paper, I would suggest, landscape. Which axis is time going to go on? Which axis is time going to go on? Time will be on the x-axis going across. The volume of gas given off will be on the y-axis. So you're going to plot a graph of time against volume. Hopefully you'll get quite a smooth curve. You might want to pause the video where you plot that graph. You're also going to, on the same graph, plot the other two results. With the experiment with the small chips and then with the larger chips. You're going to plot the same. One graph will then have 3 lines on it. Ask your teacher if you're not sure how to plot that graph. After you've done that, you're going to answer the questions that you'll be sent about the graph. Just to recap, if we have a low surface area to volume ratio, the reaction will be slower. If we have a high surface area to volume ratio, the pieces are smaller, the reaction will be faster. What you'll need to know is, why is it faster? Well, there are more particles exposed and there are more frequent successful collisions. Just briefly, also on the questions that you'll be sent, there's a question about tangents. Now hopefully your graph looks a little bit like this. Now imagine, I'm going to put a couple of data points here, 10 seconds and 30 seconds. We said last lesson that reactions are always faster at the start. Why are they faster at the start? Well, at the start, there are more particles, so there are more frequent collisions. How does this graph show that? How does it show that it's faster at the start? Well, the line is steeper. Then you can see it starts to slow down. How can you see it slowing down? Well, the line is less steep. Do you recall why we said, why does it start to slow down? Well, the particles are being used up. Eventually, no more gas is being given off. The reaction has stopped. Why does the reaction stop? Because the particles have all been used up. The reactant particles have been used up. So this graph shows that quite well. It starts off steep, then it slows down, becomes less steep, and then it becomes horizontal. But there's also something else we can work out. We can work out the rate of the reaction at a particular point. You may have done this in maths lessons. To find the rate at a particular point, if I wanted to know the rate of the reaction at 10 seconds, what I would do is draw a tangent at 10 seconds. I'm sure you've drawn tangents before, but I could draw a tangent at 10 seconds. If I worked out the gradient at 10 seconds, I would know the rate of the reaction at that one particular point. How would I find the rate at 30 seconds? I draw a tangent at 30 seconds. How is the gradient of the first tangent different to the second? At 10 seconds, the gradient is greater. What does that say about the reaction, the rate of the reaction? It's faster. At 30 seconds, the gradient is smaller and the reaction is slower. You'll do more about tangents later. Hopefully you've understood what I've said there. So, this is the first lesson on ways that we can change the rate of a reaction. The first way is changing the surface area to volume ratio. You'll need to know that if you increase the surface area to volume ratio, there are more particles exposed, so there are more frequent successful collisions, so the reaction is faster. Hopefully that makes sense. Any questions, you speak to your own teacher, and I'll get back to you shortly. Thanks very much.